Our next speaker is Anatoliy Petravchuk with the talk actions on of the derivations on polynomials and on Jacobian derivations. Please.
My talk is the action of derivation on polynomials and on Jacobian derivations. This talk is based on results obtained jointly with Alexander Kozachok. Let K be an algebraically closed field of characteristic 0, A the polynomial ring, and R the field of rational functions. I recall that K linear map D from A to A that satisfies the Leibniz identity is called K derivations on A. The set of all derivations of A is a Lie algebra with respect to the Lie bracket D1, D2 is such a commutator. This Lie algebra will be denoted by W of K. Every derivation D on the ring K can be written in coordinate form as a sum of partial differentiation with polynomial coefficients. The polynomial fi of x1, xn is the result of acting the derivations D on xi. In the case of complex numbers, this Lie algebra can be regarded as a Lie algebra of vector fields on Cn with polynomial coefficients. We studied the natural action of elements of D from this Lie algebra of all derivations on polynomials from A and on derivations from Wn of K itself by multiplication from the viewpoint of eigenvectors with polynomial eigenvalues. Recall that a polynomial f of A is a Darboux polynomial or a derivation D if D of f equals lambda of f for some polynomial lambda. The polynomial lambda is called the cofactor for D. For a derivation D, one can consider an autonomous system of ordinary differential equations of the form, of such a form, and Darboux polynomials for the derivation D are very useful in searching solutions of this system. See, for example, papers of Lieber, John Xiang, Journal of Differential Equations, and others. There are many papers about this topic. First, we consider the Lie algebra W of K, the derivations of polynomials in two variables, and denote for convenience this polynomial ring X with variables X and Y. Let F in A be a polynomial, a non-zero polynomial. The polynomial F defines a derivation df by the rule df of h equals determinant of the Jacobi matrix for polynomials f and h. This derivation df is called the Jacobian derivation associated with the polynomial f. This derivation is a Hamiltonian vector fields. In other words, note that all the Jacobian derivations form a subalgebra of the Lie algebra W of K, which coincides with the subalgebra SA2 of K, consisted of all divergence-free derivations. if for some derivation t there exists a Jordan chain consisted of polynomials, t of f1 equals lambda f1 plus f2, and so on, and the last equality t of fk equals lambda fk with such factors lambda, a polynomial from the polynomial ring into variables for some lambda in k, but in general lambda can be a polynomial, but in this case lambda belongs to the field k. Then we prove theorem 1 that there is an analogous chain in W of k of the form t df1 equals lambda minus divergence t df1 plus df2, and so on. So we see that such a Jordan chain gives us another Jordan chain, but for derivation. This we have Jordan chain in the ring of polynomials. Here we have a Jordan chain in the Lie algebra W of k with cofactors in such such eigenvalues lambda minus divergence t. The subalgebra SA2 of k is not an ideal in W of k. The later this algebra W of k is a simple Lie algebra, so it is interesting to know that the product T, the F, belongs to Si2k for an element T. It was proved in proposition 3 that this product belongs to this subalgebra consisting of divergence-free derivations if and only if divergence of the derivation t is a polynomial for some polynomial phi of t for a closed generative polynomial p for polynomial f. We also studied normalizers of polynomials in derivations under the action of W of k. Here n is a natural number on A and on itself by multiplication respectively. We consider for any polynomial f in the polynomial ring A the normalizer n of f in W of k of the form n of f is the set of all derivations such that t of f equals lambda f for some lambda in A. That is, the normalizers consist of all the derivations for which f is a Darboux polynomial. These normalizers n of f acts on the principal ideal f equals a f of the ring A. A is a polynomial ring, and the restriction of the Lie algebra n of f on this principal ideal A of f is characterized analogously for any d polynomial, for any derivation d in W of k. One can consider the normalizer of d in the Lie algebra W n of k in the form n of d equals the set of all t such that td, the product td, equals lambda d for some polynomial lambda in A. And in D is obviously the usual normalizer of the subalgebra AD in the Lie algebra W of k. These results are proved using the following proposition. Let T P derivations of the polynomial ring into variables, f a polynomial, and T of f equals G for some polynomial G. Then T d of f equals minus divergence T df plus dg. And conversely, if T the F product equals minus divergence T df plus dg for some polynomial G in A, then T of f equals G plus C. And this cofactor in some or eigenvalue, polynomial eigenvalue, because divergence of T is a polynomial. This polynomial minus divergence of T is it is a mysterious polynomial, because such eigenvalue appears while we study integrating factors for some differential equations and in other parts of algebra. In the next proposition, using this fact, let T belongs to W of K is a derivation, f a polynomial, and T of f equals G. Here, next corollary. Let T in W of K and let polynomials Fk satisfies the equalities. Have such a series of values of the derivation T on polynomials. Then for corresponding Jacobian derivation, it holds T df1 minus derivation T dfn plus df2, and the last, if T of f equals 0, then T df equals this product minus divergence T df. The next result shows that for any Jordan chain in KXA, under the action there is a corresponding analog for the action D of W of K. And here is the main result theorem for lambda in K. And now some general facts about normalizers and analyzer. For a polynomial f in A, let us define the analyzer of f in W of K to be the set of all derivations in W of K such that T of f equals 0. Lemma. Independent of independent interest, let f be a non-zero, non-constant polynomial, then the analyzer and f is a subalgebra of the Lie algebra W of K, and the submodule of the left a module W of K with rank of which equals n minus 1. For a polynomial f, let us consider the principal ideal f. So this normalizer n of f acts on the principal ideal, and if T belongs to this normalizer is an arbitrary element, then this restriction T hat of T on AF is a derivation on the subring AF, this ideal AF. All such restrictions form a subalgebra and hat of F for the Lie algebra of all the derivation this ideal AF. One can easily show that this subalgebra N of F is isomorphic N of F. The next result provides another realization of the Lie algebra of this normalizer of the polynomial theorem. The Lie algebra N hat of F is isomorphic to a subalgebra of the semi-direct product W N of K with A with natural action of this Lie algebra W of K on the polynomial ring A. And analogously, we can obtain the next proposition. Let D in W of K be the normalizer of D in the subalgebra. Then the restriction and head of D on any D on the ideal AD is isomorph to the subalgebra. This is some parallel results for action of derivations on polynomials and on other derivations by multiplication. Thank you for your attention.
Thank you very much for your talk.